Welcome to qnawire.
For the gravitational force and a circular orbit of the satellite about Earth, the force F is equal to G times the mass of Earth times the mass of the satellite over r squared, where r squared is the radius of the orbit from the center of the Earth. And since the motion is roughly circular, this is equal to mv squared over r. This is from Newton's second law and from the centripetal motion. So rearranging this equation, the speed of the satellite's orbit about Earth, v, is equal to the square root of gm over r. So we see the mass of the satellite here is not important. So if we let tau be the periodic time to complete one orbit, then v times tau is equal to 2 pi r, where 2 pi r is the distance that the satellite covers in one orbit, or tau times the expression for v, which is the square root of gm over r, is equal to 2 pi r. So from here, if we solve for r, the radius of the orbit, r is equal to the cube root of g times m, the mass of Earth, times tau squared, the square of its period, over 4 pi squared. And remember, for Earth, well, let's write down our data. So for planet Earth, we have the radius of the Earth, r, is 3,960 miles. And this is equal to 20,909, or not 20,000, but 20.909 times 10 to the 6 feet. The gravitational acceleration at the Earth's surface, g, in US units is 32.2 feet per square second. And gm is equal to the acceleration due to gravity, g, times the radius of Earth squared, r squared. And so this is equal to 32.2 into 20.909 times 10 to the 6 squared. And gm is 14.077 times 10 to the 15, and that's cubic feet per square second. We also know that the period of the satellite's orbit, tau, is 120 minutes. 120 minutes is equivalent to 7,200 seconds. So if we substitute our data into our equation above, we can find r, the radius of the orbit of the satellite. So this is the cube root of 14.077 times 10 to the 15 multiplied by tau, which is 7,200 seconds, all squared, over 4 pi squared. It's all to the power 1/3. And so we get the value for r to be 26.441 times 10 to the 6 feet. So in a diagram, it looks as follows. The radius of the Earth is capital R, and the radius of the satellite's orbit about the center of the Earth is little r. The angle between the two is theta, and the line AB represents the horizon. So the first thing we want to do in part A is calculate the altitude h. So the altitude is the height of the satellite above the surface of the Earth. So we can see the altitude h is equal to r, small r minus big R, the radius of the satellite from the center of the Earth minus the radius of the Earth. And this is 5.532 times 10 to the 6 feet. So the satellite's orbit is 1,048 miles, or 1,048 miles above the surface of the Earth. Next, for part B, we can see that the cosine of theta is equal to big R over little r. And this is equal to, we substitute our values here, 20.909 times 10 to the 6 over 26.441 times 10 to the 6. We get that the cos of theta is 0.79078. This implies that the angle theta is equal to 37.74 degrees. So the time in which the satellite is over the horizon, we'll call it TAB, is equal to 2 theta over 360 degrees. And that's multiplied by the period of the satellite, tau. And so this is 75.48 times tau, 7,200 over 360. Hence we get that time, TAB, to be 1,509.6 seconds, which works out to 25.2 minutes.